Good morning to all. I am Dr. Thayalan from Radiological Physics Foundation, Chennai. Today, we are going to talk about the principle of radiation detection. We know that we are using radiation for imaging as well as treatment. Imaging, we are using radiation in the form of general X-ray, CT scan, and mammography or cath lab. In treatment, we are using radiation in the form of telecobalt machine with gamma rays, linear accelerator with X-rays, and CT simulator with X-rays. See, what is the actual natural property of radiation? Radiation cannot be perceived by our normal senses. What are our senses? Humans have senses like seeing, feeling, hearing, tasting, and smelling. So all the senses are failing towards radiation. See, one cannot see radiation, one cannot feel about radiation, one cannot hear the presence of radiation, one cannot know the radiation with the taste, or one cannot smell the radiation. Then what we need? Then we need a device to detect and measure the radiation. So we need a device to detect and measure radiation. What we must measure? We must measure the amount of radiation as well as the energy of radiation. Then what is the devices we need? We need two type of devices. One is a detector and is a measuring device. The measuring device and the detector combined together, we call it radiation detector. It can be a radiation survey meter, it can be a contamination monitor, it can be a dosimeter. Now, where the radiation interaction takes place? The radiation interaction takes place within the detector. The detector response goes to the measuring device. Then actually it completes the radiation detection methodology. What are the various methods by which we can detect radiations? Radiations are generally detected based on certain effect which it produces. What are the effect radiation can produce? Radiation can produce ionization, radiation can produce luminescence, radiation can affect photographic film or plate, radiation can produce thermoluminescence, radiation can produce optically simulated luminescence, OSL we call it, and radiation can cause chemical effect. Radiation can also cause biological effect. So these are the various effect radiation can cause. So you can take any one of the effect as a source of radiation detection and measure the amount of radiation and energy as well as. Let us see one by one how the detectors are working on various principles. First, let us take ionization. What is ionization? Ionization is the removal of electron from neutral atom. So radiation can cause ionization in the medium we use in the detector. So these detector mediums are in the form of gas or it can be a solid medium mostly. So once the radiation does ionization, it will create positive and negative ions in the medium. So the positive and negative ions are generally called ion pairs. So radiation does ionization and cause ion pairs. These ion pairs can be measured. These ion pair can be collected by applying electric field in the detector, which gives rise to either it gives ionization current or it gives ionization pulses. The total charge collector is proportional to radiation intensity. So how much charge we are collecting? Knowing the charge, then we can say actually how much radiation intensity we have actually in the detector like that. So this is actually a small diagram to show the principle of ionization. You take, this is one detector, we call it electrode, is called anode, which is giving a positive potential. So the other side is called a cathode. It is a negative potential, it is connected to the negative of the battery. So we need a galvanometer to show the flow of ionization current. So this is filled with air or gas medium. So generally what happened, the air or gas mediums are in neutral. So when radiation comes, what happened, the air get ionized. So negative ions are produced, positive ions are produced. So both they combine together called ion pairs. The negative ions moves towards the anode. The positive ion moves towards the cathode. So the circuit actually constitutes ionization current. The current will deflect the galvanometer here. So it can be shown as a reading. So the deflection of the galvanometer is proportional to the ion pairs, which is proportional to the intensity of the ionizing radiation. So this is the basic principle by which the ion chamber is working. Now what will happen? We can vary the voltage of the ion chamber. Suppose what will happen, we can vary the voltage. So you take x-axis and vary the various applied voltage, and you can measure the current, ionization current or pulses in the y-axis. Then what will happen? When the applied voltage is 0, what will happen? The ionization current also 0. As the applied voltage increases, it also increases linearly. This region we call it recombination region. So after increase the voltage in this area, it became a saturation region. So this area is called ionization chamber region. So all the ion chambers are working in this area and given a potential of around 300 volts here. Suppose if we increase the voltage, what will happen? If we increase the detector voltage, then there will be another region comes like that. This is called proportional region, current region. That means the radiation we measure now, that is proportional to the energy of the radiation. That's why it is called proportional region. That means there is some multiplication takes place in this region compared to this. So if we increase further the applied voltage, the Geiger-Müller region takes place where the entire gas medium takes part in the ionization. So that what happened, the multiplication number goes higher number, and you will get a good response even for low level radiation. So therefore, depending upon the applied voltage, we can make ionization chamber region or proportional current region or Geiger-Müller region. So this is actually the basic characteristics of various systems we use. So the counters working in this Geiger-Müller region is called Geiger-Müller counter. The system working in the proportional region is called proportional counter or proportional chambers, or the devices working in ionization region is called ion chamber, which we use actually in most of the radiation measurement. So therefore, based on the applied voltage, we can divide the chambers as ionization chamber, proportional counter, Geiger-Müller counter like that, or sometimes in general GM counter. Generally all the three we call it gas filled chamber detectors. Maybe this ionization chamber we use for calibration purposes for linear accelerator. The proportional counter is used for energy discrimination or energy description. Geiger-Müller counter is used for low level radiations because it gives a high response even for low level radiations. Then there is a semiconductor detector also work on the ionization principle. What are the systems we use? Silicon diode semiconductor as well as the MOSFET. This also actually based on the ionization principle, but these are called solid state detectors. Let us see what is luminescence. If you take certain crystals, if you pass radiation to the crystal atoms, what will happen? The energy is converted into visible flash of light. This property we call it scintillations. That means if you give radiation to certain crystals, the crystals absorb the radiation energy and gives flash of light. The flash of light we call it scintillations. So these crystals are generally called scintillators. So later we call it scintillators. Scintillators, for example, we can call sodium iodide cesium iodide or scintillators, since they give scintillations after receiving the radiations. What we should do, the light flashes. These light flashes can be detected by using a photomultiplier tube, PMT, or photodiode. So we can record the light flashes using this photomultiplier PMT or photodiode and convert into electrical signal. This electrical signal is proportional to radiation intensity. That means whatever electrical signal we measured from the PMT is proportional to the flash of light. The flash of light is proportional to the radiation incident on the crystal. So this principle is used actually in the luminescence measurement. This type of detectors are called scintillators. So what is a scintillator? Is a solid state detector. CT scan uses actually a scintillator. So crystals gives luminescence are called scintillators. What are the type of scintillators? There are two type of scintillators. One is called organic scintillator, the other one is called inorganic scintillator. Inorganic scintillator is example sodium iodide activated with thallium. So what are organic scintillators? They are inherent scintillators available in the form of solid, liquid and gases. So they are inherently scintillators. So they can be available in the form of liquid scintillator also. How to make a liquid scintillator? You take a crystal and dissolve it in a solvent and kept in a glass vial in between 2 PMT. That means the flashes of light comes both sides, the PMT pick up the signals. For example, diisopropyl naphthalene. We call it simply DIN, and P-bis benzene. These are the liquid scintillators used which has inherent scintillation property. There are inorganic scintillators used in digital radiography, gamma camera, CT scan and PET CT as detectors. Let us see what are the detectors, scintillators we are using in each. In digital radiography, we use cesium iodide. In symbol we call it CSI. It is used in indirect digital radiography. CT scan we use cadmium tungstate. The formula is CdWO4, cadmium tungstate. Gamma camera we use sodium iodide. The symbol is sodium iodide activated in thallium. The thallium in bracket tells it is an impurity added to the crystal. Similarly, PET CT we use scintillators. Bismuth germanate, they call it actually BGO. Similarly, lutetium oxyarthosilicate, it is known as LSO. Gadolinium oxyarthosilicate, it is called GSO. These are the scintillators used in PET CT scan. Let us see what is thermoluminescence. When crystal absorb the radiations, it will store the energy for a long time. For example, you can take lithium fluoride or calcium sulfate. These are the crystals which can receive radiation and store the radiation energy for a long time. How to get the energy out? To release the energy, what we can do? We can heat the material. By heating the crystals, we can get a light emission. This light is measured, which is proportional to radiation intensity. So in short, what we should do is, you must take a crystal. The crystal should be exposed to radiation. The crystal store the energy for a long time. Once you heat the crystal, it will release the stored energy, and the stored light is actually measured and is proportional to radiation intensity. This principle is called thermoluminescence, and the dosimeter used based on the principle is called thermoluminescent dosimeters. Simply we call it TLD. This TLD is used in personal monitoring dosimeter in every setup, mostly in India. All hospitals are using thermoluminescent dosimeter for personal monitoring purposes. There is other type of luminescence called optically simulated luminescence, that is called OSL. You can take certain crystal like aluminum oxide. The aluminum oxide, when it is exposed to radiation, it will store the energy for a long time. How to release the energy? You have to expose to laser. When aluminum oxide is exposed to laser, it releases the stored energy in the form of luminescence. So that light can be measured and it is proportional to radiation intensity. So you take a crystal exposed to radiation, it will store the energy. Later it exposed to laser beam, so energy is released in the form of light. That light is measured, which is proportional to radiation intensity. This principle is called optically simulated luminescence. The dosimeter using this principle is called optically stimulated luminescent dosimeter, OSLD. So the OSLD can also be used as a personal monitors. In India we are not using it. Certain countries they are using this OSLD dosimeters. So both TLD and OSLD are called solid state dosimeters. Let us take photographic film or photographic effect. So when photographic film is exposed to ionizing radiation, it forms density. As a result, you will get latent image in the film. This latent image can be measured. How to measure it? It is measured in the form of optical density, OD, using actually a densitometer. So whatever optical density we measure is equal to log of to the base 10 I0 by IT. What is I0? I0 is the light intensity measured without film. What is IT? IT is the intensity, light intensity measured with the film. So therefore the degree of blackness in the film is related to radiation intensity. In short, take a film, photographic film, exposed to radiation, it will form blackness. This degree of blackness can be measured with optical density. To measure the optical density, one can use actually densitometer. So without film you measure I0, with the film you measure IT, then take a ratio, then you find out logarithm to the base 10, that gives optical density of the film. There is one more factor called transmittance, T. What is transmittance? Transmittance is nothing but inverse of optical density. That means transmitted equal to IT divided by I0. Probably you know that optical density I0 by IT, whereas transmittance is IT by I0. It is measured by a digital densitometer. This principle is used in film dosimetry. What category the film dosimetry belongs? Film dosimetry is a solid state dosimeter. Coming to the chemical effect or chemical dosimeter. Ionizing radiation can cause chemical changes. For example, you can take ferrous sulfate. Oxidation of ferrous sulfate to ferric sulfate. That means if you take ferrous sulfate and expose to radiation, it gets oxidized. As a result, it is converted into ferric sulfate. This ferric ion can be measured. This concentration of ferric ion is related to radiation intensity. So ferrous sulfate exposed to radiation is converted into ferric sulfate. The ferric sulfate concentration is measured, that is correlated to radiation intensity. This is called actually the basis of chemical dosimeters. Apart from that, radiation can also cause color changes in certain plastics. So by detecting the color changes, one can also find out how much radiation is exposed to the chemical. So it can also be measured and related to radiation intensity. So this principle we use actually in the chemical dosimetry. The extension of chemical dosimetry is a gel dosimetry, nowadays mostly used in most of the radiotherapy applications. Biological effect. If you take human blood, we have lymphocytes and chromosomes. So once the human blood is exposed to radiation, it will alter the lymphocytes and chromosomes. So chromosome operations can be analyzed. How it looks like that? Once the lymphocytes are actually chromosomes are exposed to radiation, it will form dicentric and ring formation. This dicentric and ring formation can be measured as a aberration score. So once you measure the score, make the score, it is a measure of radiation intensity. So simply expose the blood and see what is the chromosome aberrations and count the dicentric or score the dicentric or ring formation in the exposed blood. So that is a measure of radiation intensity. This principle is called biodosimetry. So it is very useful in the dose range of 100 millisievert to 6 sieverts. It is used in accident conditions or in emergency or where no information of radiation dose is available. That means if a person is not having a TLD badge or personal monitoring badge, the only way to find out the radiation dose is the biodosimetry. What are the type of detectors? Detectors we can make it actually in three types. Detectors that indicate number of interactions that occur are called counters. For example, Geiger-Müller counter, we simply call it GM counter. So GM counter indicate number of interactions that occur by radiation exposure. Alternatively, detectors giving information about the energy distribution of the radiation is called scintillation detector. They are also called spectrometer. For example, sodium iodide detector. If you collect energy information, then it is called a scintillation detector or spectrometer. On the other hand, detectors indicating net amount of energy dissipated in the detector by multiple interactions are called dosimeters. So the amount of energy dissipated by multiple interactions are called dosimeters. So this is what actually mostly we are using for radiotherapy equipment calibration. And based on the operation, we can divide the detectors as pulse mode detectors or current mode devices. What is a pulse mode? Signal from each interaction is processed individually in the pulse mode. Example, GM detectors. So GM detectors are operated in the pulse mode. So that's why GM detectors should not be used with equipment which gives radiation in the form of pulses. On the other hand, there is a current mode devices. What is the current mode devices? Electrical signals from individual interactions are averaged together, forming a net current signal. So what you are making? Individual interactions are averaged together and finally forms net current. So this is called current mode. So ion chambers and scintillation detectors are operated in current mode. So GM counter is operated in pulse mode. Ion chamber scintillation detectors are operated in current mode. In the current mode, the average electrical current, that is in the form of nanoampere, it is measured, that is proportional to the dose rate of the radiation interactions. The amount of current we measure is actually in the order of nanoamperes, that is proportional to the dose rate of the radiation. Current mode or rate mode measurements are preferred in high interaction rate for which there is no dead time losses. The dead time losses is the property of the detector. So where there is no dead time losses, the current mode and rate mode measurements are mostly preferred. Integrated mode measure the cumulative charges in nanocoulombs. That is called integrated mode. That means when radiation is exposed over a period, we collect the total charges released by the radiation. Ion chamber in radiotherapy, CT radiation detector, the flat panel radiation detector in a cath lab or fluoroscopy are operated in current mode. In general, we can divide the detectors for practical convenience. We use actually cast-built chamber detector, solid-state detectors, semiconductor detector, film dosimeter, chemical dosimeter, and biological dosimeter. These are the various type of detectors we use in practice in hospital setup to measure radiations for various equipment. Thank you very much for kind listening. I hope the video is very useful. Kindly subscribe and succeed. In the next lecture, we will be coming individual ion chambers, GM counter and scintillation detector elaborately. Thank you very much once again.